Hello and welcome to Chandler Science AP Physics 1 Forces Part 1. In today's lesson, we're going to talk about what a force is. We're also going to talk about systems and what that word means in physics and how we define a system. We'll also mention the types of forces that exist in our universe, and we'll also, including gravity and what a gravitational field is, and hopefully we'll have time and we'll get to Newton's laws. And if we don't get to Newton's laws in this video, we'll certainly cover those laws in the next video. If you're in my class, make sure you are taking your notes and you're going to ask one question on the discussion forums, and you're going to answer or respond to someone else's question on the discussion forums as well. If you are from somewhere else on the internet, welcome, and I hope you enjoy the video. Without further ado, let's begin. Alright, so what is a force? It's actually a quite simple definition. It is simply a push or a pull. That's it. So if you push on a car, you pull on a rope, you are applying a force to that object. So we call forces, the letter we use to describe forces in our math equations and stuff is going to be capital F. Alright, so F in the chat for forces, right? That's a thing that you say, right? That's like a cool thing. Okay, I don't know. Sorry. I tried. Yeah. So yeah, it's a push or pull. That's it. Pretty simple. The units for forces are the Newton. Okay. So let's say you have force equals 15 newtons. You put it in there, capital N for newtons. Sometimes you'll see a little arrow over the force like that, representing the fact that it is a vector quantity. All right. So it has direction. It can be up, down, left, right, positive, negative, south, east, north. You get the idea. So it's got direction and magnitude. It's a vector. The units are newtons. Capital F for the abbreviation for force, and it's just a push or a pull. All right, let's get more into details here in the following slides. All right, so before we get into the nitty-gritty about forces, we got to talk about this idea of systems one more time. I mentioned it briefly in class before, but I really want to dive into this idea here. So what is a system? All right, in its simplest terms, a system is simply an object or a collection of objects, right? You might have more than one object in your system. The user, that's you and me, the physicist who's doing the problem, defines what the system is, right? We say the system is these 3 blocks, or the system is the planet, or the system is, the car, whatever, right? You get to pick what it is, and it's going to make more sense later on when we talk about problems, but for now you need to understand that you pick the system and it's just a collection of objects, or it could even be just a single object, okay? In addition to that, a system cannot have its properties changed from internal forces from inside the system, right? Let me give you an example. You have a car going down the road, right? Here's my car, and I have a great artistic ability, so there's my car. Okay, car is going this way, okay? It's with some velocity, all right? We'll call it VC for velocity of the car. If that car is going to stop, it can't just stop on its own, right? It needs some other outside force. If the system is the car, right? So the car, sometimes I draw a little dotted circle around the system. If that's my system, the car, it can't stop on its own because no internal forces can change its velocity. That's a property of the car, right? It can't change it by itself, so it needs an outside agent, an outside force to stop the car. Can you guess where that force comes from? The ground, right? The ground from the friction from the ground is going to stop the car from moving, okay? And then the ground actually will stop car when your car hits the brakes, okay? So it needs an outside force. So inside the car, nothing you can do inside the car on your own to stop the car from moving, or to make it go faster for that matter either. So important to keep that kind of idea in mind as we go forward, okay? So let's just keep that in mind. And then lastly, we're going to ignore all internal structure of a system. So we know that the car has like moving parts, right? It's got the wheels are turning, and the engine's got like pistons pumping up and down, and all kinds of crazy stuff is going on with electronics in the car. We don't care about any of that. The system, as far as we're concerned, is a big hunk of wood, right? It's just a big object, a big block. We don't care what's going on inside. Things are whirling and swirling and pumping. We don't care about any of that stuff. It's just one big solid, hunk of object as far as we're concerned, all right? So it's a little bit about systems, and we're going to talk more about this in class when we do problems and stuff, but I just want you to have that kind of general understanding right now of what a system is, okay? Before we can talk about forces and all the different types of forces that exist in the universe, we got to talk about this idea of a gravitational field first. So what is a gravitational field? Well, the word field itself is a little confusing here because you are probably used to using the word field colloquially, like let's go play in the soccer field, or let's go dance and frolic in the fields out yonder, or whatever, okay? That's not what we mean when we say field in physics. A field in physics is a 3-dimensional or sometimes 4-dimensional space with or like matrix, you can think of it, in every direction, okay, that has properties everywhere. Okay. Now, let me give you kind of a real world example to make this easier to understand, because it is kind of weird. Think of the room you're in right now. There's air everywhere in the room you're in, right? I hope. Okay. And you can't see it, but you know it's there because you can breathe it in, you can feel it, right? Okay. Well, think about temperature for a minute. Temperature is a property of that field, the field of air in the room you're in, right? Now, the temperature may be a little colder next to the AC vent and a little warmer down by your computer because different places in the room. AC, cold air coming out of the vent, your computer gets hot, so it heats up the air around it. Well, it's the same property, but different values of that property in different locations. That's a field, right? You have one big field of air with different properties, different spots in the room, okay? So the gravitational field is similar. The gravitational field exists everywhere in the observable universe, everywhere, right? But the properties of that field are not the same everywhere. Near a large object like the Earth, for example, the gravitational field is very strong. It's a high, strong value. That's why we get pulled down towards the Earth. Next to the sun or a large asteroid or like a black hole, it's going to be really strong there too. But if you go out in the middle of space somewhere, really far away from any planet or star or black hole, it's the middle of just empty space, the effects of the gravitational field would be almost zero. It wouldn't be zero, but it'd be really close to zero because there's just nothing around you to pull you down, right? So the gravitational field is what pulls us down towards the surface of the planet we're on, or asteroid or moon or whatever, right? The bigger the mass of the object, the stronger the force is. The weird thing is that every single object in the universe has its own gravitational field. From stars and planets and black holes all the way down to you and me and specks of dust, and even atoms themselves have gravitational fields. We just don't feel the effects of those fields because it's so small it might as well be zero. So that's a little kind of overall conceptual kind of breakdown of a gravitational field. Hopefully that makes sense. If not, we can talk more in class, but it just kind of gets you this idea of what a field is. Now, as far as the Earth is concerned, that's the main gravitational field that we're concerned with. The strength of the field at the surface of the Earth is 10 newtons per kilogram. What that means is for every 1 kilogram of mass on the surface of the Earth, the gravitational field applies 10 newtons of force to that object. Excuse me. So my mass in kilograms is about 65 kilograms, right? So what's the force of gravity that I feel? Well, on the surface of the Earth, it's 10 newtons for every 1 kilogram. So I just do times 10, and I'm going to see that the force of gravity on me on the surface of the Earth is about 650 newtons, right? Now we call this the weight. Now I often abbreviate this mg, and you'll learn why I call it mg a little later, but just say that now, I guess, a little preview, a little sneak peek. Okay, now this is mass here, and this is of course weight on the right hand side. Okay, now I don't want to get really confused about the difference here. They're not the same thing. Students often confuse these, they get them mixed up, although they will assume they have the same thing. Definitely not the same thing. Mass is like how many atoms are in the object, right? In this case, my body. Okay, so if you add up all the mass on all the atoms in my body, the way we measure that is in kilograms. So we say 65 kilograms. That's the mass. Would the mass of my body change if I go to the moon? No, it wouldn't, because it's the same amount of stuff right in me. Would my weight change though? Yes, my weight would change because the gravitational field on the moon is much weaker than that on the Earth, because the moon is much smaller, right? I'm really far away from the Earth, so the further away you get from the Earth, the less effects you feel of it. But I get close to the moon, I'll feel the moon's gravitational field instead. The gravitational field of the moon is about 1/8 or 1/9, I forget now. It's much, much weaker than the field on the Earth. So my weight would go down, right? Because that field is less strong. Okay. So that's a brief kind of overview of fields. Hope that makes sense. And you get this kind of general idea, a conceptual idea of what a field is, how it's everywhere in the universe, and has different properties depending on where you are. Okay. And the one we care the most about is the one on the Earth, and it's the strength of the field on the surface of the Earth is 10 newtons for every 1 kilogram. All right. And make sure you understand the difference between mass and weight. All right. All right. The moment you've been waiting for so long, types of forces. So I said before that a force is a push or a pull, but there are different ways that we can push and pull things, right? So let's go through and discuss those ways. There are two broad categories of forces. There are contact forces and there are forces at a distance. Most of the forces we're going to talk about in this class are contact forces, but there are some that are called forces at a distance because that you can feel the pull or the push of that force without having to get close to that object. there are two that we're going to talk about, but only really one that we're really ever going to see in problems, and that's gravity and magnetism, right? You can feel the effects of gravity without actually touching the ground, right? This pin drops down towards the surface of the Earth without ever being in contact with the Earth. Where's the force coming from? Well, it's coming from the Earth, but not without being in contact with the Earth because of the gravitational field, right? So that's a force at a distance. You've all taken a magnet before and picked up paper clips or something like that with a magnet, or picked up whatever, and that force of attraction you feel, it's a force. It's pulling the metal towards the magnet, but without touching it. So it's a force at a distance. We're not really going to get into magnetism in AP Physics 1. That's for AP 2, but it is a force at a distance. Contact forces are the important stuff, so we are going to talk about those more. The first kind of contact force is tension force. Tension force is the force in a rope or a string or cable or some sort of object like that, right? Force in a rope, string, cable, etc. Right? You get the idea, okay? That sort of thing. So tension forces. So you're climbing the rope in gym class, right? You're hanging on the rope. The rope is attached to the ceiling somehow, and there's a tension in the rope, holding the rope up and holding you up, right? All right, the next force let's talk about is friction force. You all pretty much know what this is, right? This is the rubbing between two objects, essentially, right? It's the rubbing. Now, there are two types of friction forces. There is kinetic friction, and then there is static friction. I'll talk more about the differences later, but I'll give you a brief little overview real quick right now. Kinetic friction happens when an object, at least one object, is moving while in contact with another one, right? So you can think of when you hit the brakes on your car, right? You slam the brakes, your wheels stop turning, and your wheels skid across the surface of the ground. That's kinetic friction because the wheels are moving, right? Static friction is different. Have you ever tried to push a really heavy box, but it was so heavy you couldn't move it? So you're pushing the box, you're trying to get it to go, and it just won't go, right? You are experiencing static friction force. The word static means unmoving or unchanging, right? Well, we call it that because static friction is that force when you try to push a really heavy object, you can't quite get it to go, you need to get your buddy to help you out. What you're feeling pushing back against you is static friction, right? The kind of stickiness between the object and the surface it's resting on is so strong that you got to overcome that static friction force to get it to move. And then it becomes kinetic friction, right? So two types of friction, kinetic and static. We'll talk more about the differences later, but I'll give you a brief overview. So kinetic means they're moving, but static is not moving, right? You can get it to move from static friction. You can overcome the static friction, and then once you do, then you get kinetic friction afterwards, okay? But they're different. All right, then we have normal force. The normal force is the force the force from the surface an object is on. So if you have an object that's on a flat surface like the ground, and here's a box, the normal force pushes up. The normal force is always perpendicular to the surface. It's not always just up. So what if you had a box on an incline like this? Well, this perpendicular to the surface, that means at a right angle to the surface. Well, here's the surface kind of going down this way. Oh my gosh, that was bad. Try that again. Surface is going down kind of at an angle here. So that means that my normal force would be up that way, right? Perpendicular to the surface. What about a spider crawling on the ceiling? If the ceiling is here, the spider is 1, 2, 3, 4, 5. I can't do it. Okay, there's a spider, right? What direction is the normal force now? It's down, perpendicular to the surface. We label this in. Oh, sorry. I don't know why I wrote in. That's wrong. Force, capital F and little n for normal force. I've also seen students write it just capital N. Either way is fine. But this can get confusing with newtons, so I don't like to really do it that way too much. I like to write Fn. I should also mention, while I'm thinking about it, that the force of tension, we write F and then T for tension. And then friction force is F with a little f for friction force. All right? So normal force is the force from the surface you're on, and it's always perpendicular to the surface. Spring force, this is the force contained within a spring, right? If you push a spring, you compress the spring a lot, and then you let go, bam, it shoots out. That force that it pushes out with, we call that spring force. That is F with little s for spring. And then the last one is applied force. So this is like, say you are going to physically yourself go and push a block or pull on a box or whatever, something like that, right? Usually a person or some sort of agent, maybe a dog or something like that, I don't know, whatever, is pushing or pulling on a thing, and there's no other like really category to put it into. We call it the applied force, right? And we'll talk more about the gravitational force in the next video, but we don't really have a symbol for applied force. It's just usually just F. Okay. There are two equations I'm going to show you now, one for friction and one for the spring force. So the friction force equation is here. So this is force of friction equals, now this guy right here is called mu. That is the Greek letter mu, pronounced mu. Okay. Now what it means, what mu is the coefficient of friction. What the heck is that? The coefficient of friction is a number between 0 and 1 usually, although it can go over 1 in some cases, but it's usually between 0 and 1. It's a number that represents how sticky two surfaces are when they're touching each other. Okay, so if ever been on ice and it's really slippery, right? That's because the coefficient of friction is very low. It's very slick. So the closer it is to 0, the more slippery it is, right? Not much friction there. But like asphalt, we want asphalt to be pretty sticky, right? Frictiony, okay? Because we don't want cars slipping and sliding and going, slamming into each other. So the coefficient of friction of asphalt is about 0.7. It's pretty close to 1. So it's pretty sticky, okay? So the higher the number, the more grippiness, or whatever word you want to use to define it, between two objects when they're rubbing. The lower the number, closer to 0, the more slippery they are. And then, of course, we have Fn, and that's normal force, right? So the force of friction depends on two things: the coefficient of friction, or mu, and then the normal force, Fn. Now, there are absolute value bars around the normal force because the friction force can kind of go in either direction depending on how you're pushing or pulling the object. So we just usually consider it to be positive, right? Mu, the coefficient of friction, has no units. It's just a number. It's a constant between 0 and 1. And like I said, it can go over 1, but it's pretty rare. All right. And the last equation we'll show you is the spring force. All right. Now the spring force equation, you'll notice there are two absolute value bars between the x and the fs. Now, the forces of the spring here is in absolute values because, again, the direction of it can kind of change. So depending on the situation. So we just say call it absolute value, call it positive. Now this k here, this k is the spring constant. And much like the coefficient of friction, it's a constant. It's just a number, right, that represents how strong or how hard it is to compress a spring. Have you ever had one of those springs, like these big giant coils, like in a car, like the shock absorbers of a car, these big metal coils? You're trying to like squeeze one of those? It's really impossible. But no human can, like, maybe like the world's strongest man, okay, could compress that spring with his bare hands. It would take a lot of force. So a spring that strong is going to have a really large spring constant, right? Because it takes a lot of force to compress that spring. And the x here, this is the displacement from equilibrium. Displacement from, oh, that's bad writing. Let me try that one more time. From equilibrium. Equilibrium. That's an R. Okay, you get the idea. Okay, so what's equilibrium? Well, think you have a spring here. Okay, so let's say we have a wall, and then here's the ground, and there's a spring attached to this wall. All right. You ever like grab the spring and you stretch it out and you let it go and it kind of bounces back and forth, and eventually, if you just leave it alone, it's going to come to rest at a certain spot, kind of all by itself. That spot where the spring wants to be, or when it comes to rest, when it's just by itself, that's equilibrium position. Okay, so that's what the spring wants to be when it's at rest. Right here, I'm gonna put a little dashed line. This is x equals 0 right there, right? That's equilibrium position. So if I take the spring and I stretch it out, right, or I compress it, either way, right? That's why x has absolute value bars, because I can go to the positive direction x, or I can go negative direction x. I can go either direction. Okay. If I go positive direction x or negative, doesn't matter. Let's say I stretch it out this way. I stretch it all the way out to here. I stretch the spring out. I pull it out. Well, the x value now, this guy here, is going to be how far I stretch the spring from here to there, right? That's going to be my x distance. How far I stretch a spring or I compress a spring, either way, from equilibrium position. Right? And again, k is the spring constant, and then f of s will tell us how much force is kind of used to compress or stretch that spring. Okay. All right. A lot of information on that slide, so we'll stop here. In the next video, we'll discuss Newton's laws, and we'll talk more about the force of gravity. All right. Hope you guys took notes, and don't forget to ask one question on the discussion forums, and then respond to one or answer one question from someone else. Hope you enjoyed the video and you got something out of it and learned a lot. So if you have any questions, never hesitate to email me or message me on Remind, because I have no life and you are my life. So I will see you guys in the next video. Bye bye.